quickly going to recap few concepts. Okay, so all those 6 lectures, I'll just quickly kind of give you a recap. So in those 6 lectures, what you would have seen is vector spaces. So definition of vector space you would have seen. So the vector spaces that we will consider are over R, and almost all the vector spaces that we will be considering, they will be Rn for different values of n non-negative integers, and the vector spaces that we will be looking at will be R m cross n, set of all m cross n matrices with entries from real numbers. Okay, these are the two important examples for us. I suppose there were few more examples that we discussed. Then what is a vector subspace? So vector subspace, that concept is really very important. So a subset of vector space, which is a subspace, which is a vector space in itself, right? That's the concept. So suppose this is the plane R2. Then in plane R2, you would have seen that any line which passes through origin, any line which passes through origin is a subspace, right? The line passing through origin. So this is a subspace. Okay, and you would have seen that this is a one-dimensional subspace of R. So this is one-dimensional subspace of R. So what are all possible subspaces in R2? So all possible subspaces in R2 is trivial subspace, the origin, zero subspace. The second is lines passing through origin, right? So that is like any line you consider, that's a subspace. And the third example is R2 itself, the entire space R. You have to understand one thing, that even if this is a straight line which is parallel to the given subspace, this line is not a subspace, correct? This line is not a subspace. In fact, we call this affine space, right? We call this affine space. And this is not a subspace. The obvious reason for it not being a subspace is that if you add two elements from it, the addition will not belong to the same, and so on and so forth, right? So that is the issue. So for those obvious reasons, zero does not belong to this line, pink line. So a subspace always has to contain identity zero, right? Zero vector. So zero is not there. So for all these reasons, this pink line is not a subspace. Similarly, this particular thing, which is very close to linear, mod x.
Sir, I think you
So
have not shared the screen.
I have shared. I think if you join late, after I start sharing the screen, you cannot see. That's the problem, it seems. So if you use the app, I think then in the app it's visible. That's what I was told yesterday. Also, some like day before yesterday, some students were facing same problem in another class. So that's what I was told. So you try that, or if you want, I can stop sharing and start sharing again. Maybe that's easier option. So are you able to see the screen now?
Yes, sir. Thank you.
Yeah. Okay. So okay, I'll remember from next class to go for some time before I share the screen. Okay. So this mod x is also not a subspace. This is also not a subspace, even if zero belongs to this, right? So the 0 0 vector, origin vector, belongs to this mod x graph, but that is also not a subspace. Obvious reason being the negative additive inverse of these elements. So these elements additive inverse are here, but mod x does not contain those additive inverses, right? So all these examples you would have seen, geometrical interpretation you would have seen. So continuing the geometrical interpretation further, vector subspaces of R3, what are all possible vector subspaces of R3? So the possible vector subspaces of R3 is trivial subspace 0 itself, then all the lines which pass through origin, obviously, then they are all one-dimensional subspaces. Then the planes which pass through origin, so they are all two-dimensional subspaces, the planes passing through origin, and the R3 itself, total R3 itself, that is all possible subspaces that you can have in R3, and so on and so forth. So in Rn, So that is all the subspaces that you will get. The next important concept was linear span. Okay, linear span of these vectors v1 up to vk, and the linear span of these vectors is all possible linear combinations alpha 1 v1 plus so on so forth alpha k vk for alpha I belonging to R, right? I is equal to 1 to R to k. So this is the linear span, and now you see you can show this linear span is a subspace, right? Linear span is a subspace of Rm. So if you start with n vectors, so you choose k out of n vectors, then linear span is a subspace of Rm, right? So that is something that is very important thing to remember. And this thing, linear span is a subspace, is going to be one of the most important things. In fact, the fundamental thing in this course. Okay, so all the things that we will do in this course related to solving system of linear equations, this is the thing that is going to be central. Okay, this is the thing that we are really going to focus on. So we'll see today how this thing becomes really central. So that's why linear span is a subspace of Rn. Okay, this is something that you should understand. You should be able to prove. I hope this is clear to all of you. Linear span is a subspace of Rn, right? So this is a subspace of Rn, and now we have seen. So for example, take two vectors. Okay, take two vectors v1 and v2 in R3. Okay, so these two vectors in R3 you take. So what is the span of this set? So suppose I call this set A, then span of A is all alpha 1 v1 plus alpha 2 v2, where alpha 1 alpha 2 belong to R. So geometrically, what this set will be? What will be this set geometrically? Can you tell? Anybody?
Sir, a
If
plane.
V1 and V2 aren't parallel, then it will be a plane. If they are parallel, it will be a line.
So by parallel, you mean linearly dependent, independent? What?
Uh,
That's what you
yeah,
mean.
like
So
if they
I
differ
have
constant.
not given any condition on V1 and V2. Then what possibly could V1 V2 represent? Span of V1
Okay,
V2.
so if V1 and V2 are zero, that will be the trivial case. This will be zero.
Correct.
This will be span of A will be zero.
Correct.
If they are constant multiples of each other, it will be a line.
Correct.
And if they are not, then it will be some plane
So it will be a plane which will be
passing through
spanned
the.
by these v1 and v2, right? So v1,
Yeah.
v2, those two vectors. So like if you remember your 12th standard coordinate geometry, then what you are really saying is that suppose this is the vector v1 and suppose this is the vector v2. Then you are given 3 points, right? What are the 3 points you are given? The 3 points that you are given is 1, 2, 3. So the 3 points, if they are non-collinear in three-dimensional space, then there is a unique plane which passes through these 3 points, right? So the plane which passes through these 3 points is actually going to be a subspace. Why is it a subspace? It's a subspace because linear span is a subspace, and 0 is one of the points through which this plane will pass, right? So the plane will pass through origin. So it can be any plane. You take any two v1, v2, they will span a plane typically, and the plane will pass through origin. Okay, so that's the subspace that you are really talking about. So you understand the concept of linear span. And one more important concept that you would have seen is of linear dependence and independence, right? Linear dependence and independence. So what it really means is that given a set of vectors v1, v2, vk, okay, given a set of vectors v1, v2, vk in Rn, do the vectors v1, v2, vk depend on each other linearly or not? Okay, that's the question really. So these definitions, like you take a linear combination alpha 1 v1 plus alpha 2 v2 alpha k vk is equal to 0. So there is a linear dependence. you can take it further and you can define something which is called as non-linear independence, non-linear dependence. So there will exist a function f such that f of v1, v2, vk is equal to 0. Okay, so that will kind of generalization of linear dependence. So this is something that is really very important, linear dependence and independence. So v1, v2, vk, if they are not linearly dependent on each other, that means that suppose I start with this linear combination alpha 1 v1 plus alpha 2 v2 plus alpha k vk is equal to 0. Okay, so I consider this linear combination of v1 v2 vk which gives me 0. Then this implies, if this implies that all these alpha 1s are actually 0, then I'll say that v1 v2 vk are linearly independent. Okay, linearly independent. That means that there does not exist a non-trivial linear combination. What is trivial and non-trivial linear combination? So this is a trivial linear combination. Trivial linear combination meaning a linear combination of vectors which will get you to 0. Okay, so for this particular linear combination which gives you 0, you cannot have non-zero scalars such that this will happen. So this seems really little weird, but if you read and if you think of it like 3-4 times on your own, then you will start realizing what this really means. And the linear dependence, the way people define is something, the set which is not linearly independent is dependent. That means that you will have such a linear combination alpha 1 v1 plus alpha 2 v2 plus alpha k vk is equal to 0, but that does not necessarily mean that all the alphas are 0. Okay, so that is something that is really very important. So some of the alphas will be not equal to 0. So strictly speaking, linear dependence is actually the generalization of concept of the linear multiple. Okay, so if two vectors are linear multiple of each other, so I can draw them here. So in R2, for example, in R2, suppose this is my vector v1 and this is my vector v2, then v1 and v2 are really multiples of each other, right? So v1 can be written as some alpha times v2. Here the value of alpha will be obviously negative and less than 0 based on the diagram that I have done, right? So alpha is actually the scaling factor between v1 and v2. So what you see here is v1 minus alpha v2 is equal to 0. So you have a linear combination of vectors v1 and v2 which is going to 0, like here. But that does not necessarily mean that these coefficients alpha 1, alpha 2, alpha k are 0. Here you have alpha 1 is equal to 1 and alpha 2 is equal to minus alpha. Okay, so that's what really means that v1 and v2 are related to each other through a linear relationship. Okay, so what is that linear relationship? The linear relationship is defined by this linear combination, and the alpha i's that are sitting there, they are actually telling you what is the linear relationship between these vectors. Okay, so that's why this linear dependence concept actually is generalization of the vectors which are scalar multiples of each other. So if there are multiple vectors together, are they related to each other linearly or not? That's the question you are asking, right? So the question, are they related to each other linearly? So what is that linear relationship? The linear relationship that you're talking about is actually the linear combination, trivial linear combination. I think somebody's mic is on. If you can just there's a lot of static coming. Yeah, Ankit Singh, can you please mute yourself? So this is about linear dependence and linear independence. So once you have all these concepts together, then the last thing I think that you would have seen is linear functions. So what is linear functions? So linear functions are basically functions t from Rn to Rm, okay, such that every vector v goes to tv. That's the rule. And what are the conditions that this linear function has to satisfy? T of alpha 1 v1 plus alpha 2 v2 is basically alpha 1 t v1 plus alpha 2 t v2, right? So that's that's the condition, okay, for a function to be linear. And in particular you would have seen this, that when when m is equal to 1, then inner product, the inner product that we define, inner product also gives rise to linear function, right? So they are called as linear functionals, right? So I think that's what the terminology that was used in the recorded video. So they are linear functionals. And then we defined something which is called as affine functions also. And if I remember correctly, you would have done this. You please remind me if that result was there in the video lectures or not. That any affine function can be written in the form of ax plus b. For every x in Rn, there exists a in Rm cross n and b is in Rm, such that any affine function p of x can be written like this. Is that correct? There was
Yes,
such a
sir.
result proved in the video lectures, right? And that affine function becomes a linear function. This affine functions becomes a linear function if and only if this b is equal to 0. Is that right? That is also something that was done in the lectures. So if
Yes,
b is
sir.
0, then if b is 0, then you get a linear function. So every linear function has this representation of a matrix, right? So every linear function can be represented by a matrix. So matrix itself is a linear function. So I think that is the point where we will start. So I hope this is a quick recap of all the things that you would have seen in those 6 lectures. If you have not seen those lectures, I will once again say that please see those lectures. Make sure that you understand everything that is being discussed in those lectures, because that is something that I will not like to cover again. Okay. So is there any doubt about what is been discussed so far, or in particular if you have anything to say about the lectures that you have seen? Okay, so if those things are clear, then we move to the next topic. One of the important topics is solving system of linear equations. Okay, solving system of linear equations. So this is something that is really very important, and almost many real life applications, whatever problem you are trying to solve eventually boils down to a solving the system of linear equation. Okay, so how to solve a system of linear equation is a very important problem. In AI ML perspective, one of the most important reasons why one would like to solve a system of linear equations is because you are interested in solving the regression problem. Okay, so in regression, linear regression, or in the linear regression problem, you will see that eventually the problem will be formulated as a system of linear equations that you want to solve. So the system of linear equations that you want to solve can be of any type. So right now, what we are really going to do in last in the few minutes that are remaining in this class. Hello. Ishan, you don't know where the lectures are posted. They are posted in the Teams. Okay, so please see the lectures. Okay. I have posted the links, YouTube links for the lectures. Please click on the link and watch the lecture. So the solving system of linear equations. Okay, so this is one of the most important problems that you will encounter. Uh, and using this we will see. Okay, so the first thing that is to be understood is that what is given. So what is given a matrix A in Rm cross n and a vector B in Rn. Okay, given a vector B in Rn, find if exists x in Rn such that Ax is equal to b, such that Ax is equal to b. Okay, so this is what we are really interested in. So is that okay? So this problem is clear. So I am considering this problem in its most general sense. I have a m by n matrix. So I have a rectangular system of linear equations. Okay, so this is a square system A and B. Okay, so maybe if you want to see the Ax also, this is the square system, rows is equal to column. If m is greater than n, then I have a tall system. Okay, so Ax is equal to b. So this is the type of system Ax is equal to b that you encounter many times in real life problems, especially in the regression problems. So we'll try to understand how these systems are and what it really means. And the third type is obviously the wide one. So you have a like this, you have x like this, and you get b like this. Okay, so these type of problems, these type of problems you will typically find in regression. These are square systems, Ax is equal to b. These are square systems, and these type of problems, they are called as underdetermined. Okay, so the name here is underdetermined. The reason for that name is that you have less number of equations than the unknowns that you are able to that you want to compute. Here it is overdetermined. So overdetermined really means that you have more number of equations than the unknowns that you want to find. And this is square. So here you have exactly same number of equations as the unknowns that you are trying to compute. So these are the different names, or this you can call tall, or this you can call wide. So this wide one, underdetermined one, actually you will find this type of things appearing in compressive sensing problems. Okay, so that is where you encounter such systems. This typically you will find in regression problems. Ax is equal to be the tall one, and the square one is of course present in many things. So many partial differential equations, when you try to solve numerically using finite volume or discretization methods, you end up with system of linear equations which are square. Okay, so there are different applications where you end up with different types of system of equations. But the geometrical meaning, the beauty lies behind understanding the geometrical meaning. Okay, so if you really see this, then we will focus more on these Ax is equal to b. Okay, so b is in Rm, and what you are really looking at is find x. Okay, what you want to do, find x. I will write it down as x1 up to xn in Rm. Okay, you find this x. That's what we are trying to say. So suppose, okay, suppose there is an x. Suppose there exists an x in Rn such that Ax is equal to b. Okay, so Ax is equal to b. So how do I write this A really is critical. Okay, so suppose I write down this A as A1. So let me write small case letters, A1, A2 up to An. And what are these A1, A2, Ans? They are basically the columns. So A1 is the first column. So if you want, I can make these brackets bigger. So this is what the matrix A really looks like. So here A1, A2 up to An, these n vectors belong to Rn, are columns of A. Okay, columns of A. And you have this vector x, which is nothing but x1, x2 up to xn, and this is actually equal to b, right? So Ax is equal to b. This is how I am really seeing Ax is equal to b. So now you have seen matrix vector product, right? So I think matrix vector product was discussed in the video lectures that were given to you. So you have a matrix A, and when you multiply the matrix A with the vector on the right hand side, so basically what interpretations you can give to this matrix vector multiplication? So the one interpretation that you can give to matrix vector multiplication is you multiply first row by this vector, right? So inner product interpretation you can give. So in the product, what happens? You are having inner products here. So row 1 transpose into the vector x. So suppose this is matrix A, and R1 transpose, R2 transpose are the rows. R1 transpose, R2 transpose up to Rm transpose. There are m rows. Then one interpretation that you can give is R1 transpose X, R2 transpose X, so on and so forth, Rm transpose X, right? Rm transpose X. That's the interpretation that you can give. So this is typically how you immediately understand the matrix vector product. But can you say this is also same as x1 a1 plus x2 a2 plus so on and so forth xn an, where these ai's are the columns which are actually these vectors. Can you see that the matrix vector product ax is actually this also?
Yes, sir.
Hmm? So the first column A1 gets multiplied by x1. In all these, you look at R1 transpose X. There also you will see that you are having first 1/1th entry getting multiplied by x1, 2/1th entry getting multiplied by x1, 3/1th entry getting multiplied by x1, so on and so forth up to the point m1. M1th entry will get multiplied by x1. So all those entries I put together in the first column and I multiply that with x1. So I multiply x1 into this plus same thing x2 into second column entries, so on and so forth, xn into last column entries, an. Is that fine with all of you?
Yes, sir.
I hope this is clear with everybody. Because this is very important. This way of understanding matrix vector multiplication will give you a very interesting idea. This will give you a very interesting idea about system of linear equations. So if this is clear, then what we really are saying? Suppose there exists a x in Rn such that Ax is equal to b, then what you are saying? You are really saying that you can write down b as a linear combination. What is the linear combination? This is the linear combination. X1 into first column plus x2 into second column plus xn into the last column. So what you are saying is that if there exists an x in Rn such that Ax is equal to b, that really means that vector b, this vector b, can be written as a linear combination of columns of this matrix A. That's what this is really saying. So what does this mean geometrically? This means that for a b in Rm, so given b in Rm, so this is the b that is given to you. One can write b as a linear combination, okay, linear combination of columns of A. Linear combination of columns of A. This is something that is really very important. So I hope you see the connection. So when you are given a system of linear equations Ax is equal to b, when you are given a system of linear equations Ax is equal to b, and you say that there exists a such that Ax is equal to b, what you are really saying is that b lies in the column span of A. In other words, what all systems of linear equations Ax is equal to b are solvable? All those b's which lie in the linear span. And what is the solution of the system of linear equations? The solution to the system of linear equation is that linear combination that you can find out, which will enable you to write the given vector b as linear combination of a1, a2, an. So basically what you are doing here by solving Ax is equal to b, you are checking whether a given vector b belongs to the linear span of columns of A1. So what we do, we give a special name to this linear span of columns of A. So linear span of columns of a matrix A is called as column space of A, or you will see later on for obvious reasons, it will be called as estimation space of, okay. So this estimation space terminology will come when we will see the regression equivalent of this problem of solving system of linear equations. But for linear algebra perspective, it is called as column space of A. Okay. So since column space is a linear span, it is a subspace. Can you tell me it is a subspace of what? R. What is it subspace of?
M.
Rm. It is a subspace of Rm. Okay. So there are n vectors given to you from Rm. There are n vectors given to you from Rm. Those n vectors are arranged as columns of matrix A, and you are looking at all possible linear combinations of the columns of this matrix A. That is called as linear span. Okay, so this is the linear span. So the subspace is called as linear span. Because it's a finite dimensional vector space and the subspace of a finite dimensional vector space, the column space will also be finite dimensional. Okay, so the column space is also finite dimensional. The dimension of column space of A is actually called as rank of the matrix A. Okay, so what is the rank of matrix A? Rank of matrix A is actually equal to the dimension of column space of A. Okay, so that is something that is very important. So rank of a matrix is really very important concept, and you know, like you would have used it many places. But what does rank really mean? Rank really means that it's the dimension of the column space of A. Okay, so now what happens if rank of A is equal to m? What will happen? What will happen if rank of A is equal to m?
Unique solution.
No, so from the point of view of subspace, what will happen? So unique solution will be like
It will span the entire space.
it will span the entire space. So first we'll go step by step. So rank of A is equal to m means that column space of A is actually equal to Rm. Do you understand that? I think some similar theorem we had proved that if you have a subspace of the dimension equal to the parent vector space, then that subspace is actually the parent vector space. So the column space of A will actually be equal to Rm. What does that mean? For any right hand side B, so which implies that for every B in Rm, one can always find an x in Rm such that Ax is equal to B. Why? Because what you are saying, the column space of A is actually the entire space Rm. What does that mean? Every vector in Rm can be written as a linear combination of columns of A. That means that for every possible right hand side B, you can always find out x such that Ax is equal to B. So far so good. This is fine. So now why do you think the solution is unique? Somebody said unique solution. Why is the solution unique here? Somebody was saying unique solution, no? Somebody wrote in the chat square system. Why is that?
Uh, we proved in the lectures that any vector which is linearly dependent on a set of linearly independent vectors, they can be uniquely represented by those set.
Correct. But the key word was that any vector which is in the span of linearly independent vectors, right? Have you said anything
Yes.
about linear independence of columns of A?
Uh,
Sir, because
yes.
rank of A is M here.
So what?
Sir, and rank of A is dimension of the column space of A.
Correct. So what is the dimension of column space of A? That is M, right?
Which is equal to the whole space dimension.
That is Rm. That is Rm,
Or
right?
basically, it's a basis of Rm.
No, it is not basis of Rm. Why is it basis of Rm? So I'll give you an example. The example I give you is 100132. What is the column space of this matrix A?
Sir, R2.
Column space of A is R2. Column space of A is equal to R2. So for any B belonging to R2, I can always solve AX is equal to B where X is in R3. Can I do that? Always? Can I do that?
Yes, sir.
So do the columns 1, 0, 0, 1, 3, 2 span R2? Yes, they span
sir.
R2. Is this set a basis of R2?
No, sir.
So how can you say that you have a unique solution, it will be a basis? You cannot say that. What we are saying here is only thing that if columns of A span the entire space Rm, then you will always have a solution, because having a solution means that being able to write B as linear combination of columns of A. Are you able to do that or not? Yes, we are able to do that. So this does not say anything about the columns of A being basis of the space and so on and so forth. Do you agree with this?
Yes, sir.
Is that fine? So now you can see the example. Now you understand where you are making confusion between M and N. Now can you slightly modify what will happen if M is equal to N? Now you say what will happen if M is equal to N? That means that if I have same number of rows as columns, that's the condition that I'm giving you, extra condition, I'm giving you that, then what will happen? If rank of A is equal to M, the matrix is Rm cross M, then what will happen?
Then there will be unique solution.
Why? Correct. There will be a unique solution, but why now?
They will be linearly independent.
Correct. They will be linearly independent. Why? You are right, but can you just give one more statement? Why they will be linearly independent?
Because rank is N.
That is already given. So rank
The
is
set
N.
itself is basis.
The set will be a basis. Why it will be a basis? So step by step. So A belongs to Rm by M. Okay. Column space of A, I will just write it down for short, call A, is entire Rm. Okay. So what does that mean? Columns of A, which we will say A1 up to AM, span Rm. Okay, the span of columns of A is entire Rm. That's what the first statement really means. So you have a collection of M vectors which span the entire M dimensional space Rm. What does that mean? That vectors, so this set has to be a basis of Rm. So the columns will be basis of Rm. Okay, the columns will form a basis of Rm. And if the columns form a basis of Rm, then what will happen? Then for any B in Rm, what will happen? For any B in Rm, there will exist a unique linear combination. There will exist a unique linear combination unique linear combination x1 up to xn, so that is m here. I will just write it down in terms of vector such that ax is equal to for any b. So you not only are guaranteeing the existence of the solution, but you are talking of uniqueness of the solution also. So this result which says that the column space is entire space, that guarantees you existence of solution. Solution will always exist if the column space is Rm. Do you see that point? Is that point clear to all of you? Now just see what is happening here. By taking M is equal to N and saying column space of A is equal to Rm, you are actually saying that the columns of A form basis of Rn. Then any vector B in the base, any vector B in Rn can be written as a unique linear combination of these vectors, basis vectors. So you get a unique solution. What is happening? Suppose you have A which is equal to this M by N, N by 1, M by 1 over a determined system case. What is really happening, you tell? What is really happening? Will you always have a solution? What will happen if rank of A is you think about this situation, you tell.
So can you repeat what we have to
So
tell?
what will happen in this particular case? The question is, now I have a matrix A, I have a matrix A with this. So how many columns are there? N number of columns are there. So A1 up to AN, N number of columns are there. Okay, M by N. And here the situation is such that M is greater than or equal to N. Typically, M is really very bigger, very big than M. Okay. So now what will happen? When you look at the span of columns of A1, A2, AN, would you ever be able to cover the entire space Rm?
Only if they're equal. If M is
No, if
greater
they are
than
not
N, we
equal. M is strictly greater than N. M will have
yeah
100 rows and
yeah
N will have only 5 columns, 100 by 5 matrix.
yeah we won't be able to cover the entire space.
So what is the maximum dimension that you can cover in
Um,
R100?
N, the
N,
number of
correct?
columns.
N.
Yeah.
Number of columns N. So now you understand, here, given a matrix, you see the columns as collection of vectors in the space Rn, the columns. So the maximum subspace of Rm that you can cover is the n dimensional subspace. Do you understand that? So if that n is bigger than m, then the maximum you can go is up to Rm, obviously. So you can cover the entire space Rm. If m is equal to n, then obviously the same thing, you will reach up to Rm. But if m is greater than n, that means that the size of the vector, the length of the vector is bigger than the number of vectors in your collection, then you will not be able to cover entire space. Even if the columns of A are linearly independent, you will not be able to cover the entire space. So for example, you see here a 3 by 2 example. I will take 1 0 1 0 0 1. Okay, this is the matrix A that I have. What will be the span of columns of A? What will be the span of
It's
columns?
gonna be the XZ plane. So the
It will be
second
the x.
coordinate will
Correct.
be 0.
It will always be 0. So what is the linear span? Linear span will be alpha 1, 0, alpha 2 plus alpha, alpha 1 plus alpha 2, right? For different values of alpha 1 and alpha 2 belonging to R. So what is the property? The property is that second component is always 0. So y is equal to 0 is actually the subspace. So y is equal to 0 is the xz plane, right? So this is the xz plane. So this xz plane is what you will cover by this columns of A, right? So now if I give a vector B, if I give you a vector B and I say write that vector B as linear combination of columns of A, will you be able to write it? Will you be able to write it? Not always, because if the vector lies outside the xz plane, then you will not be able to write. But if the vector lies inside the xz plane, then in fact you will be able to write it, and you will be able to write it uniquely also in this particular case, because the columns are linearly independent, right? So the columns are forming a basis for the subspace, and if the vector is coming out from the subspace, then you can write down the vector as a linear combination of columns, unique linear combination, because it's a basis. Do you understand the logic? What is happening here? So what is happening? So yes, do you have any doubt? Okay, so what we are doing, let us summarize. Okay, so you are trying to solve Ax is equal to B. Doesn't matter if A is small, like tall or wide or square, it doesn't matter. The first thing, if B belongs to column space of A, then there is always a solution. Then there exists a solution X always. Okay, so A is in Rm by n. Okay, so B is in Rn. So there will always exist an X in Rn such that Ax is equal to B. Is that fine? Is that fine? So this condition geometrically is telling you the guarantee of existence of solution. The solution will exist if B belongs to column space of A. And if columns of A form a basis of column span of A, then for a vector B in column space of A, not only the solution exists because it's in the column space, the solution is unique. The solution is unique. Okay, so here I am using the word the. Okay, so this is to show the uniqueness, and here I am using the article A to show only the existence. We don't know about the uniqueness, right? So here in this particular case, you will see in this particular example, suppose I give B to be equal to 1, 1, right? What is the obvious solution here? What is the obvious solution? X. Correct? So that A times X is equal to B. I am looking at the first two columns, E1, E2. So any vector B in R2 is what? Alpha E1, alpha 1, E1 plus alpha 2, E2. Is any vector alpha 1, alpha 2, is it? So I just use this alpha 1 here, alpha 2 here in the solution. So I take any vector and I will just put 0 for the third column, and I will get this solution. But do you think this solution is unique here? Because B is in the column space of A, like I said, there exists a solution. I actually gave you a solution. But is this solution unique?
No, sir.
So what is the other solution?
Minus 2, minus 1, 1.
Minus 2, minus 1, 1. So if you take X to be equal to minus 2, minus 1, 1, then that also is a solution. So only one extra solution, or is that it?
No, sir, there are more.
So how will you find those?
The 4, 3 minus 1.
Huh?
4, 3 minus 1.
4, 3 minus 1. 4, 3 minus 3. Okay. 4, 3 minus 1. That is fine. That will be a solution. That's it? Only 3 solutions? Or will there be any?
Infinite.
There will be infinitely many.
We can
Yes.
fix a Z and
Any
find.
linear combination of the two solution.
Huh?
Any linear combination of the two solution again is solution.
Any linear combination of two solutions is a solution? No. You take x is equal to 1, 1, 0 and you take x is equal to minus 2, minus 1, 0. Just add them up. Will that be a solution? Check and tell me.
Sir,
Huh?
sir, so like we can say that there are infinite solutions. Like if we look at the second picture of matrix multiplication, where I can write the three components of x as x1 times the first column, x2 times the second column, x3 times the third column is equals to b. So
Correct.
now I can write, basically I can break the last column into 3 times the first column plus 2 times the second column,
Correct.
and it will become x1 plus 3 times x3 times the first column plus x2
Yeah.
plus 2 times. So now I have another set of equations, that is x1 plus x3, 3x3 is 1, and x2 plus 2x3 is 1. So I have three variables, two equations. I can take one as a free variable, and
That's right.
according
So
to
this
that
is the
solve
method
it.
that you learned in first year linear algebra, right? In maths 2 you would have learned this. Is it not, Kshitij? I think Kaviraj also replied saying
Yes,
the
sir.
same. But now that you are looking into this as a linear function, there is another interesting picture. Okay, so what is it? So the time is running out. I have only 5 minutes. So let me try to complete this quickly. Okay, I'll repeat this. I'll repeat this once again. Okay, next class. But this is very nice and we are almost there. Okay, so let x in Rn. So I'll not use x. I'll use another letter z. So let vector z in Rn be such that az is equal to 0. 0 vector. Is that okay? Let there exist some vector. So z is equal to 0 is obvious, correct? So there exists at least one vector z in Rn such that az is equal to 0. You take z is equal to 0. This is obvious. But there may exist more than a vector 0 such that az is equal to 0. In other words, what I'm saying is that if the columns of A are linearly dependent, then there exists a non-zero vector z such that az is equal to 0. Yeah, that's the definition of linear dependence, right? You take linear combination of vectors, the vectors being columns of A, you take the linear combination which is going to 0. That does not necessarily imply that the coefficients, which is nothing but the vector z, is equal to 0. So if the columns are linearly dependent, then I will have a non-zero vector z such that az is equal to 0. Otherwise z is equal to 0 is always there. It doesn't matter linear dependence or independence. So now I'll use linearity of A. Okay, use linearity of the transformation A. Okay, how do I use? So let x in Rn be such that Ax is equal to B. Okay, so given a vector B and A, I have found out one particular x such that Ax is equal to B. Then can I say that A into x plus z is also equal to B? Can I say that? Do you see how I have used linearity of A here? A of x plus z is actually equal to Ax plus Az. In fact, what I can say is that Ax plus alpha z is equal to B. Is that right? Linear multiple of 0 is still 0. It doesn't matter. So if I find out one vector z, then all the linear multiples of z, that means that the entire one-dimensional subspace, I can choose in the direction of z, and A into x plus alpha z is equal to B. Now you see what you are doing here. All the solutions that you are giving me here, this solution, and this was the particular solution which gave you Ax is equal to B. You see all these solutions you were getting by x alpha into minus 3 minus 2 0. You see, you will always be able to find out alpha. You can find out alpha for this. You can find out alpha for this. You can always find it out. So in this particular case, I think alpha will be equal to minus 1. In this particular case, I think alpha will be equal to 1. Am I right? Maybe I'm wrong. No, this is right? Yeah, alpha is equal to 1, alpha is equal to minus 1. These are the values of alpha that you found out such that you get x into x alpha. And what is this vector? This vector is our z, the one that I just defined. Az is equal to 0. So what we are really going to do is we are going to I'm finishing. Just give me 1 minute. Last definition I'm giving you. So I will define something which is called as NA, null space of A, the set of all vectors Z in Rn such that Ax is equal to 0. Okay. And what you did here is that you chose any vector in the null space Z and you just added x plus z, right? So you chose any vector in z. So I really do not need to take alpha then once I define null space, because if z is in the null space, then alpha z obviously is in the null space, right? So that's what I have done. So any particular solution, plus NA is the set of all solutions. Okay. At the ending note, do you think you have done something like this already somewhere? In Maths 1, at least those who are BTech students, dual degree students, in Maths 1, have you done this somewhere? CF complementary function plus particular integral is the solution. Exactly.
Yes, sir.
So there also you use the same concept, right? You found out the homogeneous equation. You, for a linear constant coefficient differential equation, what did you do? You found out the homogeneous equation, found out all the solutions of homogeneous equation, and then you found out a particular solution, added them together, and you get the entire solution space, right? Why? Because the solution space of a constant coefficient homogeneous second order, third order differential equation, that actually is a subspace. It actually is a vector space in itself. So that's why this same logic, same concept applies there also, right? So this is the idea, very interesting idea. So let us stop here. I don't want to continue further. The time is up. In the next week, we'll continue our discussion from this point. Okay, so please go through these lecture notes once again. Okay, anything you